Okay, today it's heavier duty vector stuff, but we could do a little bit of review, wouldn't hurt you. So let's have you do one vector where you work it all the way through, where you take, this is vector v, and it's going to be 2i plus 3j minus k. And I'd like you to figure out the little hat for me. Remember what that is? Okay. And I'd like you to figure out for me its column form. And one last thing, figure out for me if I have vector m and it's 2i minus j plus k, then what's the angle that would be between those two? Okay. So figure out, realistically, I'm not going to ask you to figure out v hat because you're going to have to, this will take a lot longer. When you're done, if you finish the theta problem, then I'd like you to try to figure out a vector in the same direction as v, except 20 magnitude instead of the magnitude it has right now. Okay, try to make one with a magnitude of 20, but make this your first priority. If all you have time for is that, that'll be okay. I'll pause for a second while I give that a shot. Okay, in class we showed what those vectors look like in 3D, and now the final answer comes down to this. You go inverse cosine of the dot product of them, which would be, what was the dot product? 0. Ooh, unusual. Over, let me think. Well, 0 over anything. Just think about that. Doesn't matter what I put down on the bottom, does it? 0 over anything, it's going to be 0. So the inverse cosine of that, and it turns out to be 90. All right. So that made a right angle, but it's kind of a weird in 3D space right angle. All right. So now if you did have a chance to do this one, you should have said 1 over the magnitude, because if we want to make its magnitude 20, first what we do is find the unit vector. So that's 1 over the square root of 2 squared, which is 4, 3 squared, which is 9, and 1 squared, which is 1. And that makes 14, was it? And then you can write this as a column or a position vector. I'm going to write it as a position, 2i plus 3j minus k. There we go. That is the unit vector. But if I want it to be 20, I just have to times it by 20. How many of you would have had that right also? Okay, good. Then you're up to date so far. Now what are we doing today? Today is completely different. Today we are taking a vector and basically pinning it down so that it has to be in a certain place. I told you before, if we had a vector that looked like this, that it would be the same exact vector if it was here, or here, or here, or here, or here. Shouldn't have that little curve in it. I apologize for that. These are straight lines. Okay, it's the same thing. Because why? Because it needs the same what and the same what? It's the same magnitude and the same direction, and this is a vector. Okay, so if I want to move it to somewhere else and make it stay there, then we can do that. And there's a way to do it by making it have an equation for that vector. So let's just talk about the difference between a point and a vector. Do you get a point that doesn't really have much information? 2, 1. It's just there. It's over 2, up 1. It's a dot. I can't tell if a vector goes through it, starts at it, ends at it. It could go at any direction. Okay, there's not much info there. But this vector has a lot of info right here. That tells me if vector v is, could you hit the door for me, please? If vector v is that, then I know that it's over 5 and up 2. There's a dot there, but I know a lot more than that. I know a direction. I know where it started. I know where it ended. I know all the points that are in between it. Do you get how I have a lot more information in a vector than just a point? Okay, but it's still not an equation. This is not an equation. I can't get that to be, well, I can get it to be an equation, but it's not an equation like you're used to, where we had things like this. back in the old days, you'd have a y-intercept and a slope. Okay, and that y-intercept basically is like where you start, and then you go up 2 and over 1, and up 2 and over 1. Remember what I'm talking about there? You need a starting place, and then you kind of where you go from there. Well, there's a equation form for vectors, and it's not like that. Here's an equation for a vector. X, y, and then you say its starting point. Well, if it's this vector, it has a standard starting point of what? 0, 0, in fact. And then you add some factor that'll tell you kind of where to go from there, right? And that factor is lambda, and then 5 over 2. Now I want you to think about this. Do you get how this is more than a normal equation? A normal equation has an x and a y in it. This also has a what in it? Lambda. And lambda is kind of like time. It's kind of like a parametric. Yes? Okay, and just to clarify, if we wanted to, we could even add the third dimension by going like here, like actually I should have had a J in there. I apologize. Just hold on. I know you're asking something different, but I'm trying to make a point here that this, by adding a third coordinate here, this would make it three-dimensional. And then I could say x, y, and z, and 0, 0, and 0, and then 5, 2, and 2. That's making it three-dimensional. This does not add another dimension like that, but it adds time to it. That's what it adds to it. Can you guys stop messing around, please? It's very distracting for me. All right. So if I'm going to take this, I'm going to go back to when it only had 2 dimensions. Just keep it relatively simple here. Except I do need to add that. And this really should be a J, not like a fatal flaw or anything. Hold on. Whoa. I can't explain why that's happening. Here, I'll just go like that. Fine. Okay. Now, if I wanted to write the equation for this same vector, but I wanted it to move to a different spot, do you get how this would need to change? Its starting place needs to change. All right, so what if I said I want to take the same exact vector, but I want it to have its tail end not be at 0, 0, which is what it is right now, but I want its tail end to be at 2, 1. Do you get how easy it's going to be to change that? All I have to do is change 0, 0 to 2, 1. There. Now I've got a vector that has to start at 2, 1, and it will end at, well, a new place. Do you get how it ended right here at 5, 2, but now that I'm moving it, it won't end at 5, 2? All right, if this is truly an equation, it should be good for giving me some points. What if lambda is 0, like when you start your vector? If lambda is 0, do you get that this whole thing will just go cancel? And I get 2, 1 for my first point? Make sense? And then what if lambda is like 1? It's like a counter. So if I say I want to go over 1 vector length, I stick a 1 in there, and let's see what point we get. X, y becomes 2 plus 1 times 5, which is what? 7. And 2 plus 1 times 2. So my new point is 7, 3. So now I can tell that my vector would start at 2, 1, and it would end at 7, 3. All right, let me see if you really got that. So I'm going to give you a new vector, 6i plus 9k, j, sorry. I keep wanting to use k. And that's going to be called vector q. My question is, I know what that looks like. You know what that looks like. But what if I moved it so its tail was at 2, -4? So we want the vector to start at 2, -4. Two questions for you. Number one, what's the equation for it? What's the equation for the vector? And where is the head of the vector? Once you've got the equation, it'll be easy. Time is 0 or time is 1. Lambda is either 0 or 1. I'll pause for a second while you give that a try. Okay, so here's how this should work. To start with, it's an equation, and vector equations always start with this. Always, always, always. Vector equations do. And then we need the starting point, which is really simple. We start at 2, -4, piece of cake. Then we need a plus lambda and kind of like directions on what direction to go. And this tells me that. And so 6 and 9. There we go. Raise your hand if you had it right. Okay, cool. Now, watch how we get the starting and ending point. Well, we already have the starting point right here. But if I wanted to see that in terms of lambda being 0, if I stick in lambda 0, this whole thing cancels, and therefore my starting point is 2, -4. If lambda is 1, if you stick a 1 right here, then my new head end is not, the head end is no longer at 6, 9. The head end is now at 2 plus 1 times 6, 2 plus 6, 8, and -4 plus 1 times 9, which makes 5. Raise your hand if you had 8, 5 as the head end of your vector. Okay, good. Now, how does it get more complicated? It gets more complicated because there's more than one form. That was called vector form. But actually, these are incredibly easy if you understand what's going on. If I need parametric form, do you remember that parametric form just had an x equals equation and a y equals equation, and it had it in terms of t? It's just that now, in the context of vectors, it's not a t, it's a what? It's a lambda. Then I bet you already know the answer. How many of you already know what you think the answer is? It is as easy as you think. Go ahead, tell me, Mr. I. What do you think it is? X equals what? Yeah, keep going. It's that easy. 2 plus what? 6 what? Lambda. It's just like being in the old days, the parametrics always had to have a t in them, right? Now you just have to have a lambda in them. See what you did there? So what's the other one? Yep. If you said lambda 9, I would have taken it too. 9 lambda is the normal way to write it, but all it is you just multiply it out. Across the top here, x is 2 plus lambda times 6. And then across the bottom, y is 4, -4, sorry, plus lambda times 9. There we go. We just changed it to what form? Parametric form. Now remember, when we're doing parametrics, one of the main things it's good for is doing time. I want to put this in the context of that bowling ball lab that we're going to have eventually here, where you're going to have 2 bowling balls that have vectors. What are you going to want the bowling balls to do? You're going to want their vectors to overlap. Well, any idiot can like roll a bowling ball this way, and another person can roll a bowling ball that way and make their paths cross. But what's harder? Making them hit the same point at the same time. Exactly. Do you get how time being involved is going to help us? If we can set our time equals 0 is when we start the ball, in both cases, and if we can get our vectors to, at time, let's say 1.6 or whatever we figure out it needs to be, if at time 1.6 it's right here, and on this equation it's also right there, then that means that they will both be in the same place at the same time, which means we should be able to make them hit. Okay. So that's why adding time into this is good. All right. So now there's one last form. What we changed to here was parametric form, but there's one last kind. that same old graph, you know, I'm sick of that same old graph that you've been doing since like middle school. That is actually rectangular, or there's a new name for it. It's a new old name. It goes all the way back to René Descartes. Cartesian, very good. So Cartesian form, same exact thing as rectangular form. We actually looked it up today because we weren't sure it was exactly the same. It is. They are the same. They can be used interchangeably. So rectangular form and Cartesian form mean the same thing. So when you see Cartesian form, sounds really fancy. It's just, it has x's and y's in it. How do I get this to only have x's and y's in it? It's the same as last time. Remember how we had to get it from parametric form into rectangular, so we had to get the t's out of there. Now what do we got to get out of there? Lambdas. We get the lambdas out of there, we'll only have x's and y's, and we can have one equation that has x's and y's in it instead of two equations that have three variables, x, y, and lambda. We'll just have x and y. Now let me tell you, you can do this in two different ways. And what I'd like you to do is, just so that when you look at the answer key, it will be easier for you, because honestly, both ways would work. But solve this one for lambda, solve this one for lambda, and then set them equal to each other. So I'll show you what I mean. I'm going to solve the top one for lambda. I'm going to subtract 2 from both sides, and I have x minus 2. And then I'm going to divide by 6 on both sides. I divide by 6, and I have lambda. Lambda is x minus 2 over 6. Do that same exact thing for the second equation. Then you'll have lambda, and they can obviously be interchanged for each other. And you can write one equation that doesn't have lambda. So you should be solving this right now. This is baby algebra. You can do this, no biggie. Raise your hand when you got it. All right. I'm going to take you. What did you have?
I have y plus 4.
Yep. Y plus 4 over 9 equals lambda. Good. And if lambda is equal to lambda, you can plug this in right there, and you'll have x minus 2 over 6 equals the other one, y plus 4 over 9. Now, do you agree we could solve it for x? Or we could solve it for y? You don't have to. We usually write it in that form right there. It's done. Now, I know there's another way you could do it. I'm just trying to tell you the answer keys are going to look like that. And if we had stuck this into the equation where lambda was, this right there, it would have been solved for y. We could have done it that way. But this is the way you're going to see on your keys, so same thing if you solved it for y. All right, any other questions about that? Okay, so there's one last topic. But first, before we go on, I'd like to give you the same kind of challenge. Let's say it's at 0, 7 is the start of, I wanted you to take this vector and move it to have a start there. Here's the vector I wanted to use. Negative 6i plus 2j. And I want vector r to be moved to have its starting point be here. But I want the answer in Cartesian form, which is going to realistically make you do all three forms. I would start with vector form, change it to parametric, because I want the answer in Cartesian. All right, pause for a second. Let me try that one. All right. I was asked if that first letter was an I. I will clarify, yes. The first letter is an I. It was negative 6i plus 2j. I'll pause while you finish that. So here's what you should have done. You should have said, all right, here's how you generally make these equations. I need a start point right there. Oh, I know the start point, 0, 7. Done. Plus lambda, and then can I just slap in those? Yep, you can, because that tells me the direction. It's negative 6 and 2, and that's it. This time I did not ask you to figure out the head end. We already know the tail end, of course. It's at 0, 7. But the head end, if you wanted to do it real quick, you would stick in what for the lambda? A 1. All right, good. So next is, how do you change that to parametric? You just multiply across the top. You got x equals 0 plus lambda negative 6. So 0 minus 6 lambda. And y will be across the bottom. It's not really multiplying, but you take it from the bottom. Y equals 7 plus 2 lambda. There we go. Is that what I wanted? No, I wanted what? Cartesian. So then we have to solve each of these for lambda. So it's x divided by negative 6 is lambda. And this one is y minus 7 over 2 is lambda. And then I set lambda equal to lambda x minus 6 equals y minus 7 over 2. Why is this good? Because it's simpler. It's only got x and y in it. Why is it bad? Because it's simpler. Oh, is there something wrong? Negative 6. Let me see if you're right here. Yep, thank you. You're right. Why is it bad? Because it lost data. That equation can't tell where it starts, where it ends. That equation goes forever in both directions. Is that really what's happening? No, it's not really what's happening. What's really happening is it only starts here and it ends there. Okay, so that is a problem with these Cartesian ones, because they don't have all the info about where to start and where to end, because it's kind of like time, and it's missing the time element. All right. So what's next? What's next is I say here is where I want this vector to be. I want it to be at 1, 6, and I want the head end to stop right there at 8, 14. How on earth are you going to do that? Well, you always start the same way. If you want an equation, what's in that first box, or the first parenthesis? X and y. Yep. And what's in the next one? 1, 6. Simple as that. Plus lambda. And all I got to figure out is that. And it's not an 8 and a 14. Think about this. When we had them before, they were a vector that was going, and it was telling us what direction to go. We need to figure out what to put there so that when we put in a 1 for lambda, it will give us an answer of 8, 14. So here's the easy way to think of it. You just have to take the x minus the other x, 8 minus the 1, which is 7, of course. And then you have to take the 14 minus the 6, which will be an 8. How do I know I'm right? If that's 7 and that's 8, then when I stick in lambda is 0, I better get 1, 6. Well, put a 0 here, it's going to cancel everything. So yeah, it worked. Okay, if I put in a 1, what am I supposed to get? 8, 14. If I stick in a 1 right here, 1 plus 1 times 7 gives me 8. Yay. And 6 plus 1 times 8, 6 and 8, 14. Yay, it's working. Okay? So if I give you the head end and the tail end points of a vector, it's really not that hard to write the vector equation for it. And then if you really want to be fancy, you can write it in parametric form from there. You learned how to do that. Or Cartesian form, which is a fancier name for what? Rectangular. Same graphing system you've always been using. Which one's the weakest? Cartesian, because it doesn't have what? The starting point and the ending point, or you could say time. All right, good. I think you learned something. That's good. So your assignment for today, it's going to go, all of them are easy. Honestly, you're going to, if you understood what we did today in class, there's nothing like really confusing here. Okay, so problems 1 and 2 are just the same concepts. And I want you to understand that the rest of the problems are the same concepts as the first page. It's just they say it differently. Like when they give you this, aren't they giving you a point and a vector? It's the same exact thing. They just say it differently. So don't freak out because it's got to be different because it says it differently. Nope, same thing. The only thing it's not being really clear about is that it says it passes through that point. Wouldn't you agree if it starts at that point? It passes through that point. So it's easiest to think about it that way, that this is the starting point. If you want to write start here, that's the starting point. Red on orange, classic combo. And then this same thing, this is a start point. I want you to also get that when they give you 2 points, they technically are supposed to tell you where it starts and where it ends. Because do you get, if a vector is going the exact opposite direction, it is different? Because the direction's a big deal. So these should say from the A to the B. So we're going to put a little 2 in all of them. A to B, A to B. If it ever isn't told, then just take the first point they give you as where you want it to start, as in the tail end, and the head end is where it ends. All right. This one, notice they're giving you a funky form of it. What form are they giving you? Parametric. It's like you're halfway through the problem. You already got vector form, and then you got parametric out of it. So now they want you to go backwards and say, if this is vector form, what's the parametric? Well, it's really simple. It's x, y equals, can you tell from this what the starting point was? And if you couldn't tell, could you tell somebody, what would you stick in for lambda to figure out what the starting point was? 0, exactly. And then you need the lambda, and then you need not the ending point. This is not the ending point. This is the point, this is the directions on which way to go. And again, you should be able to go backwards. It's just the exact opposite of what we were doing before, where we had a vector equation and you made it into parametric. Now you're just going backwards. Okay, that's enough that this is honors pre-calc. You should be able to make that leap easily. All right, on to this one. The only thing that's confusing about these is they throw in r and mu as the variables. Here, in our normal vector equations, we have x and y here. Don't let it freak you out that it says r equals. It's okay. It's the same exact thing as if they had an xy there. And this mu can be a lambda, or the lambda can be a mu. All right, so it's the same. Don't let that bother you. It's the same questions. All right, and this is where I feel like the assignment's just getting a little bit long, and so you may skip number 6, the very last one. It's just it's a repeat of find Cartesian, which realistically makes you find all 3 forms. I think you've had enough problems at that point, so you may skip number 6. Okay, and that's all I have for you for today. I think that's a doable assignment. Get it done. All right.